In our last video, we learned that electrons repel each other, and because of that, after we get a certain number of them nearby, they start pushing the next ones out, and they have to go further and further out from the nucleus of the atom into what we call shells. And we use that knowledge to begin building our periodic table. And we learned that in the innermost shell, we could have 2 electrons, and in the next shell out, shell 2, we could hold 8 electrons, and in shell 3, it will hold 18 electrons. And in this picture here, we have only 8 electrons in this outermost shell, which will hold 18. So before we add another electron to that shell, we need to look at rule number 4. Rule number 4 is that nature will only allow a maximum of 8 electrons in the outermost shell. And we call that outermost shell the valence shell. So whatever happens to be the outermost shell at the time, nature will only allow 8 electrons to exist there. And this is a very stable point in nature. So both neon and argon are very stable elements. Some people call them happy elements. But if we scoot back one element from argon, for example, this is chlorine, it only has 7 electrons in its valence shell. Now, it would very much like to be as stable as argon or neon by having 8 out there, but only has 7. And so what might happen here is there another element from way over on the other side of the table, one that only has a single electron in its outermost valence shell, can oftentimes mix with one of these that's only one short of being full. And so hydrogen and chlorine can mix here and make hydrogen chloride, for example. So this is how elements mix in nature because of this desire for the elements to be comfortable, or if you will, or stable by feeling like they have 8. So from chlorine's perspective now, to chlorine, it looks to him like he has 8 in his outermost shell, making him very happy and stable. Another example of this, without getting into too much chemistry, would be if we scoot over 2 from neon over to oxygen. You see there are 6 electrons in oxygen's valence shell, and it would love to have 8. So in this case, 2 hydrogens can come floating by, and they can come and attach to oxygen, and now oxygen feels like he has 8 electrons around. It makes him very happy or very stable. And so this becomes a very stable compound in our universe, and this is known as H2O, or water. Okay, enough of that about chemistry. I wanted to talk about that mainly because I wanted to really emphasize how stable these guys in this column are with the 8 electrons in the valence shell. It's full, so these don't combine with anything else. Like all these other combinations we showed things combining, these will not combine with anything else. And we call them noble gases because they won't combine. Now, why did I explain that to you? Well, I explained that because if we go back to this picture here and we look across the chart, we see helium over here, and helium has 2 electrons in its outermost valence shell. But if you recall from our analogy with the neighborhood, this shell, the neighborhood shell, or shell 1, only can fit 2 electrons. So actually helium has its valence shell full as well. So it too is a noble gas, and it won't combine with anything else. So in order to make our chart stay consistent, we're going to just adjust things a little bit and scoot helium over to this side of the chart. Now I'm going to make some room here so we can add some more elements to our table. And remember, we left off here with argon with the valence shell being full in quotes, meaning there's still room in there as far as the other electrons are concerned, but because of that rule of nature, it is full at this point because it's the valence shell, and you can't have more than 8. Now we can bring in our next element here, which is potassium, which has a very interesting abbreviation. But you can see our new electron is out here in shell 4. We have a lone electron in the valence shell, so that can go into column 1 in our shell 4 row. And we bring in the next element, which is calcium. You can see we have 2 electrons out in the valence shell, so that can fit nicely in column 2. And at this point, we'll note that if we look into shell 3 of calcium, that there's only 8 electrons in that shell. And we know that shell 3 can actually hold 18 electrons. as far as the electrons are concerned in that shell, they can have 18 of them without running into each other too much, so there's that much space. But we've not allowed the electrons into that shell because of our valence shell rule, which said when that was the valence shell, we can't have more than 8 electrons in there. But now the valence shell is shell number 4, and you can see it only has 2. So when we bring in our next element, we can see that the new electron, the extra electron, is not out here in shell 4. There's still only 2 out there. Instead, it has infilled in here to shell 3 and became the 9th electron in shell number 3. It wants to be as close to these protons in the nucleus as possible, so it will take the nearest position to the nucleus as it can, provided it's not breaking any of the rules of nature. So when we decide where to put this in our table, we can start by putting it here. But this creates a problem because this column is actually for things that have 3 electrons in the valence shell, and this one only has these 2. So that kind of messes up our idea of grouping things by column. So in order to keep consistency in our chart, we have to kind of scoot the chart over to make room for this one. Likewise, when we add the next one, we have to scoot it over as we continue to infill electrons in there to shell 3, until finally we have all 18 electrons in shell 3, and shell 3 is now full. So now on the next element, when we add a proton and the associated electron, we have no choice other than to add it out to the valence shell. And now we have 3 electrons out in the valence shell on this guy, 1, 2, 3, which is consistent with this column of having 3 electrons in the outer valence shell. And now we can just continue filling valence shell, which is shell 4, out until we have, again, 8 electrons out in the valence shell. And now we have to stop. By nature's rule, we can't have more than 8 in that outer shell. And so we can just continue following this pattern, and we can continue to build out our table. Rather than continuing to write those out with characters, I grabbed this picture off of Wikipedia of the periodic table that is in a form that's probably a little more familiar to you, and you can see that the pattern continues with another infilling kind of process down here with these elements, which fit in the chart right in this spot right here. But once we have the elements in the chart and we understand how the chart was built, we can now talk about trends and know more about each of these elements just based on where they happen to be arranged in the chart itself. For example, we already talked about the noble gases over here with their full valence shell, that they don't interact with anything else and don't combine with anything else. And next to that, this group we call the halogens. They have 7 electrons in their valence shell, so they would love to connect with something or grab another electron to fill out their outer or their valence shell. Oftentimes they connect with items out of group 1, which have a lone electron way out on their valence shell. These become very reactive because of that. They're uncomfortable having that one electron way out there. Another trend here is that things on the left side of this kind of angled line here, those are all metals, and the things to the right are non-metals. Things to the left tend to be solids, except for mercury there. Things to the right tend to be gases. Things in the middle of the chart are very dense and are very good conductors of electricity. They only have 2 electrons out in their valence shell, make them very good conductors of electricity. Those are just some of the ideas of trends that exist throughout the chart. And we could go on and do an entire video about that, but it really hopefully demonstrates how by putting the elements in a table, a periodic table, and understanding how that table is created can then lead us to be able to know more about these elements and the trends and the characteristics of those elements based on their position in the chart.